little introduction last week. We looked at the different logic gates, AND, OR, NAND, NOR, etc. What we're going to do this week is have a look at combinational logic circuits. So this is where you might have 2 or 3 inputs working an output. You might have a system with more than one output that you want to design a circuit for. So we're going to look at how we produce a truth table from a given logic circuit. So that you might need that if you had a logic circuit somewhere and you wanted to understand how it worked, you might want to sketch out the circuit and then write out a truth table. And truth tables also come in to reckoning when you want to test your circuit that it operates as you intended. Because what you would do is systematically test every input combination in your truth table and make sure the outputs are doing what you designed them to do in terms of those inputs. So more about that in a little while. Then we'll look at how we can produce a logic circuit from a given truth table. Later on, we'll include something that's a typical real application, not too complicated, but we'll do something around a boiler heating system. And then we're going to look at how the discovered logic design circuits can be simplified using something called kernel maps. We may get to reducing the circuit to utilize one type of logic gate, but we may not get that far this week. Okay. Everybody happy for me to move on? If you aren't able to speak, then shout up in the chat if you've got an issue, okay? Or just quickly put the sound on and back off again, I don't mind. Right, so what we're going to have a look at is the truth table for this circuit here, and I'm going to go through like a step-by-step approach as to how we can work out what the truth table would be for that circuit. So I'm going to put a different color to black on, go for red. So we've got a truth table of 3 inputs, A, B, and C, and 1 output Q. Okay, and all this writing over here for a minute because that's the result. But if this is A here, then that gate is an inverter. So out here we'll have not A. And then this is an OR gate. So it's going to OR this B and this not A together. So here we're going to get not A or B. And then this gate here is AND. So I'm going to write that in there. OR, and this one is a NOT, just to remind you. Okay. Therefore, final output must be not A or B from this line, and all of that is ANDed with C. Everybody follow that? So we could write that out as kind of shorthand description of what this circuit does. Is if we have not A or B and C, we'll get an output on Q. And in Boolean, we write it like so. Not A plus B and C. So not A plus B in brackets and C equals Q. When you bracket a term in Boolean algebra, it's like brackets in mathematics. You have to do what's inside those brackets first. So you have to OR not A with B first, and then AND it with C afterwards. So there's an order of precedence in this Boolean algebra. Okay, everybody happy that you've followed that? Yeah. Right. What I'm going to do for you now is just I don't know whether you signed up for any of you, but I'm just going to show you that circuit on the multi-sim online system. I've got that one on there now. Just going to stop that screen broadcast for a minute and start up. If you can have your truth table in front of you for what we just done, and then we're going to check against that truth table that this circuit does what we designed it to do, or what we said it should do. So what we've got here then, you can all see that, yeah? So we've got three switches here, three binary switches representing A, B, and C. And on A, we've got a NOT gate feeding into another OR gate. The B is directly into that OR gate. So out here, we should get A, not A or B. And then that not A or B is ANDed with the C down the bottom. I'll put an LED on the output so we can see when it turns on. What we've got to do now is check every possible line across that truth table and whether we get the output that was intended. Yeah, I've got a different circuit up on my other screen at the moment. So for the first column, for the first line of the truth table, if all the three switches are 0, we have no output. So that's correct. And then the next line is turn switch C on. We should get an output. Help if I turn the interactive simulation on. So turn C on, we get an output. Yeah. So when we're inputs at 0, 0, 1, we get an output, and we should do. So you can cross that one off, the first two off the list, or tick them as being checked. The third column is just B on its own. We shouldn't get an output, and we don't. The fourth column is B and C on together. And we should get an output, and we do. Okay. And then the next one is just A on its own. Shouldn't get an output. Then A and C, and we shouldn't get an output. And then A and B, we should not get an output. And then A, B, and C, we do get output. Yeah. So that's how you exhaustively check the digital circuit. You must check not only that it turns on when you want it to turn on, but it doesn't turn on when you don't want it to turn on. So you're checking not just what you want it to do, but you're making sure that it doesn't do what you don't want it to do. Yep. Everybody get that? Good. Okay. Right. I'm going to do something here with this next slide on the other thing, because I've got the wrong file up here and I've got the answers down before you've had a go at it. So I'll cover them up. Right, I'm going to share the other iPad screen again. Right, so on your next page, there's one there for you to have a go at. So can you complete the truth table for that circuit, please? Okay, I'll give you about 5 minutes, and I'm going to set it up on the simulator as well, so we can see that whether it does what it says on the tin. Right?
Oh yeah.
Have a go. Okay, so in summary, then we've we know that we got to do B and C first, and then OR it with not A, so you end up with that. And then we built our circuit on the system, and we checked every line in the truth table to make sure it worked as it was. Okay, what I want you to do now is have a go at this one. I've just covered up the answers for now. Here we've got an inversion on the output here. So we got because we got a NAND gate on the output. You want to build a truth table for that. First of all, build the truth table without that inversion on the end, and then so we got an extra column here in the truth table for not C. This is not C here. Yeah, ANDed with A or B. So without the inversion, if we didn't have the dot on the end, the output would be not C and A or B. So if you work out what that column is, ones and noughts, and then apply an inversion to the output afterwards. So everywhere you've got a 0 in this column, you put a 1 in that column and vice versa. And then you've got the actual output. Okay, so have a go at that and see if you can do a truth table for that. No. Yeah. So in this statement here, C, not C, ANDed with A or B. So what that suggests is anywhere where C is turned on, not C will be off, we're going to get a 0 out of the AND gate. Yeah. So we can put zeros in all them four because C is on. And then in the other ones, we're looking for either B, although C isn't on, we've also got to have either B or C. So we haven't got B or C in that top one, so that's a 0. But here we've got B, sorry, B or A. Here we've got A, so that's a 1. Here we've got A and B, so that's a 1. So that's your output if you had an AND gate on the end. But we haven't got an AND gate, we've got a NAND gate. So we've got to invert the output. So what we do is just go down this column. Everywhere we've got 0 in here, we put a 1 in here, and vice versa. Yep. So that is the behavior we'll be looking for when we build the circuit in multi-sim, as that last column. Because it's Q, it's not C, and brackets A or B, all inverted. So that line across, right across the top there, means the last thing you do is invert the whole output, which is done with that inversion ball on the end of that AND gate. It's an AND gate. All right. Just name them gates. Or not NAND. Stands for not and. All right. So I'm going to stop sharing there for a minute. Have a look at the circuit on multi-sim. So when all our A, B, and C are all off, we got an output, we've got an LED on. So the first one is okay. When we put C on its own, we should still get an output. We do. When we have B on its own, we don't get an output, correct? When we have B and C on, we do, correct? When we have I on its own, we shouldn't. We don't. I and C, we should. We do. I and B, we shouldn't, and we don't. And A, B, and C, we should have a 1, and we do. So that's checked every line of that E3 input truth table against the specification we had in the first place. Yep. Okay with that, everyone?
Yep.
Who's listening? Yep. So it can be a little bit tricky and it takes practice to get used to doing those. But once you get there and then you test it and does it do what I wanted to do. So I thought this online multi-sim was pretty good for that, really. You can pay for more facilities, but for what we're doing at the moment, that seems to be enough, these digital circuits anyway. All right. So I'm going to go back to sharing the other screen now. We're going to have a look at something else. Right. See that truth table there? Okay. We're going to look at is building a logic circuit from that truth table. Yeah. So if we look at this, the last column's the output Q. Get out of the way. Last column's the output Q, and its condition is stated for all the 8 different possible combinations of 3 inputs. Yeah. So if you have 3 inputs, you always get 8 combinations. That's 2 to the power of 3 is 8. Yeah. One way to tackle this is to say, right, everywhere where we've got a 1 in the output column, so that's here, here, and here, we can write a Boolean expression for that column. So we can say, to get this 1 here, we need to have I on, not B, because it's a 0, and C. And in this row, A needs to be on, B needs to be on, and C needs to be off. And then lastly, we need A, B, and C on. Yeah. And so we need a 1 in the output column if any of those conditions are met, any of these 3 conditions. So what we need to do is OR these all together. So our final expression is that Q is equal to A and not B and C, or A and B and not C, or A and B and C. Yeah. So that's our expression. We've got 3 different routes. 1, 2, 3 different possible combinations that will turn that final output on. 1 or 2 or 3. All understand that so far? Okay, I'll move on to the next bit then. I'm going to take that expression with me. I've already done that up here. One I prepared earlier. So there's our expression. All right. So if we want to draw a logic circuit for that, we can do, let's go do first of all, once things start getting a little bit more complex, it's sometimes useful to have the inputs in a vertical lines down the screen so that you can come off them like worse, called a buzz bar. So we need to AND all these 3 together firstly. So we want I, we want, and you always put a dot on where there's a connection. We want not B, So we put an inverter in, and we want C. I'm going to AND those together. Yep. So they've done that one. Then we need to AND these three together. So again, we take off A. We're going to take off B. And we're going to take off C inverted. And then lastly, we've got to AND all three together. So here's our gate. A, B, C. So here we've got A, not B, and C. Here we've got A, B, and not C. And here we've got A and B and C. All we're left to do now is OR all three together with a 3-input NOR gate, OR gate, to get our final output here, Q. Yeah. We follow that?
Pretty much.
Okay. Yeah. So, you know, that's not too difficult. Now, one thing I was going to say was, would you believe me if I told you that that can be done with two 2-input gates? It can be simplified to two 2-input gates.
I believe whatever you say, Mike.
You'll believe whatever I say, but looking at it, I mean, it wouldn't take a genius to realise that we've got A and B twice here, and there's some obvious simplification you could make. I'm not going to even attempt to try and teach you Boolean algebra. I'm going to try and show you a way in which this circuit can be simplified. But first of all, what we'll do is we'll take an early 15 minutes. Tell you what, I'll take an early 20 minutes till past. I'm going to build that circuit on multisim so we can just check it off against the truth table. And then when we've simplified it, we'll build that circuit as well and show that it does exactly the same thing. Fingers crossed. All right? Yeah? So take an early break, 20 minutes, get a quick drink, and I'll see you back here at past. All right?
All right. See ya.
You leave yourselves in the room if you want. You don't have to jump out if you don't want to.